All right, it's already 7 p.m. We will start. Could you please confirm that you can hear me, see me, and see my slides? Could someone please confirm that you can see me? You can hear me? Okay. All right, then we'll start. There are still people coming in. Okay. So, good evening and welcome to this second week doubt clearing session of this NPTEL course. There are so many people still coming in. Let us wait for some time. There are still people coming in. Okay, in any case, we will start. Good evening. My name is Saptarshi De. I am a PhD scholar at IIT Bombay. I am working in the field of electric machine design, and I will be taking this course on, not the course, the doubt clearing classes on of the NPTEL course, Electrical Machine 1. So this is the second week, which is on practical transformer, how to, what are the losses in a practical transformer, and how to model them in the equivalent circuit so as to analyze the losses. So first I would like to address the doubts that you might have in this course. In these videos that you have been asked to watch in this week. So before we start, could some of you raise your hands who have watched all or some of the videos? Just not necessarily all, some of the videos also. If you have watched, could you please raise your hand? Okay, there are some. Okay, lower your hands. So first, I will discuss your doubts from the lectures. So you can unmute yourself and talk. One thing is the decorum we follow here is you unmute yourself, talk, and again mute back. Okay, you can now unmute yourself and ask questions if you have some doubts in the lectures. In this week or last week, anything. Who have not watched a single video? I just want to see. everyone has watched the videos and still no one has any doubt. My goodness, how will I write on this? All right, then it looks like people are mostly interested in the problems. So many people coming in. Can someone unmute yourself and talk at least so that I can know you can talk? You should be able to talk. Can someone please talk?
Hello.
Yeah, okay.
Hello, sir.
Yes, okay. So what it appears is that you don't have any doubt in this week or last week lectures, right? Okay, then I guess I will start with problem solving. Yes, you can go ahead and talk. You can go ahead and talk. Yeah, go on. I have some logistical problem here, but you can go and talk. No doubt the lectures are too easy. Okay, then let me ask you, have you understood how the hysteresis loss was calculated? Someone's trying to say something?
By using the open circuit test, they are calculating, sir.
Open circuit test what? Sorry. What is the question exactly?
Actually, you asked how the hysteresis losses is calculated. Means we conduct an open circuit test, then we will find that hysteresis and different losses.
No, that is how you find. But
Okay.
Okay, I will reframe my question. My question is, why does the hysteresis loss at all happens? Because see, eddy current loss, it is understandable. The flux is changing, eddy current is
okay. Okay, sir. You are asking about the hysteresis losses.
Yes, how is it happening? How at all is it happening?
Actually, it is a non-reversal of magnetic flux lines, sir. That's why it's happening, sir.
No,
actually,
that's not a definite answer. That's okay. But can you show me, or can you explain how at all there is a loss? You remember these curves were there?
Hysteresis curve, sir.
Hysteresis curve, and from there some energy supplied. No?
Hysteresis loop, sir.
Those equation, why at all the area represents the energy loss, those things? Harshit, I can't hear you. I can't hear you, Harshit. Your voice is tremendously breaking.
Hello, sir. Can I answer the question, sir?
Yeah, go on.
Sir, hysteresis loss occurs, sir, because when the first we apply, sir, magnetic field, so the magnetic poles are not oriented, but as they are get fully oriented, so when we decrease the field, they do not have deoriented. They do not have tendency to go to their original position. So there is some residue left, magnetic residue. So the hysteresis loss happens.
No, what you said is why at all there is hysteresis. But my question is, why at all is there a loss? Why at all is there a loss? See, the thing is like this. Suppose you have a curve like this, psi I, okay? Psi I curve is same as BH curve. Whether you are writing psi I or drawing a psi I curve or a BH curve, it doesn't matter. They are basically the same. Both of them represent the material property. Arshit, please mute yourself.
Yes.
So when you have an inductor whose BH curve is given by this, and you supply that inductor using a variable voltage, let us say. So what is the voltage equation? The voltage equation is, can someone tell me what is the voltage equation here? Quickly. I can't hear you, Harshit. Someone else?
IR plus LDI upon dt.
IR plus LDI dt, but that is true, that is not wrong. But a more general way of writing is d psi dt, because when you are writing psi equals Li and hence d psi dt equals L di dt, you are assuming that your inductance is constant, but inductance might not remain constant, isn't it? Especially when we are talking about saturation and hysteresis, inductance will not remain constant. So this is a more general way to write d psi dt, which is Faraday's law. Now, if I multiply current on both the sides, I will get this. I d psi dt. And if I then integrate both the sides with respect to time, I will get I squared R dt plus integration over I d psi. Right. Now suppose I am integrating for some time 0 to t. At t equals 0, this voltage is 0, okay? So what is happening? See, if in this equation, there are three components. Left hand side, there is one, vi dt. Quickly say what is this is. What is integration over vi dt? This is nothing but the electrical energy input. Electrical power is Vi. When I integrate Vi over time, that is energy. What is I squared at dt?
B squared by 2.
Eddy current loss.
Where are you getting eddy current here? This is R, this is L, this is resistance loss. Resistance loss, simply loss in this resistance, I squared R. I'm giving a DC which I'm increasing. Where is eddy current coming from here? Loss in this resistance. So I gave some energy, this much of energy got wasted. So what about this? What happens to this energy? This energy remains stored. If for the time being, let's say if I write d psi equals L di, I will get L I di, which is half Li squared, nothing but the energy stored in an inductor. But we will not write it this fashion because we are not sure whether L is constant or not. Or in other words, we are trying to generalize this thing. So integration over I d psi. Suppose at steady state, this is my current. Okay. Then integration of I d psi. Can someone tell me which area does it represent? Area A or area B? Integration over I d psi. This is psi, this is I. Can someone tell which area is it representing? Area A or area B? I will write psi and I here for you. This is psi, this is I. Quickly.
Area A.
No, not area A. When you have a y versus x curve like this, the area under this is given by y integration y1 dx, integration over y dx. But here you have I d psi. So it is this area. the other area. This is the area ID shy. Okay, so you push some energy using this voltage source and stopped here. This much of energy got stored in the magnetic circuit. Okay, now I will remove these lines. Now the material property is such that its hysteresis, its BH curve is like this. It has hysteresis. It has hysteresis. So we came back from here, something like this, let us say. Now if I reduce, we went in this fashion. Again, if I reduce this voltage V, and again look at these equations, apply these equations here. When we came back at this point, this is the stored energy. So initially, now if I say, initially what we had is this much was the stored energy, right? Then we came back and our stored energy reduced to this, say this. And again I make the current zero. So what I did is I had a circuit, I gave some energy to it and again took it back by reducing the voltage. There is some loss, definitely. There is some loss definitely here. But what about this energy? This energy which got stored in the magnetic circuit, that never returned. It was lost as heat energy. So this area is exactly the energies. Do not even think that this area is proportional to energy. No, this is exactly equal to the energy. This equation says that. Exactly equal to the energy that is lost. This is the hysteresis loss. You see, if there was no hysteresis, if there were no hysteresis, but if there still were this saturation, we would have gone like this and come back like this, and there would have been no hysteresis loss. Saturation is still there, right? So that is why the area inside the hysteresis curve will give you the loss per volume per stroke. Stroke means in one time period. All right. So this,
Sir, how the charge, the stored energy is dissipated, sir, in the form of what, sir? It never will be dissipated or not, sir?
it is dissipated in terms of energy, heat energy. The core becomes
Heat
hot.
energy.
Hmm.
Oh, the core becomes heat.
Yeah.
Okay, sir. Okay, sir. Thank you, sir.
So this is the most interesting thing that I found out in this lecture. That's why I thought I would discuss. Last week actually I got a lot of doubts from the attendees. Okay, anyway, if you just want to look at these questions. Okay, in any case, you can ask question anytime if you want. All right. So you can see the question, right? Consider a 65 kVA, 50 Hertz transformer with 250 primary turns, 125 secondary turns. The rated low voltage is low voltage side voltage is 500 volt. Questions are that estimate the rated primary voltage in volt. This is easy. Someone should tell this. So I have the high voltage side here, low voltage side here, 250 and 125. Said that the low voltage side voltage is 500 volt. So what is the high voltage side? Quick.
One thousand volt.
1000 volt, only two times. Just make it two times. Okay. So estimate the rated primary current in ampere. How should I approach?
Rated power divided by primary voltage.
Rated power divided by primary voltage. So what is the rated power?
Rated power is 65 kVA.
What is the unit of power?
Unit of power is apparent power. Apparent power in kVA.
Why should I take apparent power? Yes, you are right. That it has to be the primary current I1 is 65 kVA. This divided by the rated voltage here, which comes out to be 65 ampere. Is it? So everyone is clear about this, why this is kVA and not kilowatt? Anyway, last class we discussed. Shovit is there, Shovit. Shovit was quite active last day. No? Okay. And what will be the secondary current? Secondary rated current.
It is a given two-way. First, in a relation V1 by V2 is equal to I2 divided by I1.
Let's see one thing. Do I need to apply so many formulae? V1. Can I simply say that the power will be same?
That means rated power rated divided by V2. That means secondary current.
V2 we can do, and we already have the current. So
that means
voltage is half. Current will be twice.
Yeah.
Into 2, 130 ampere. Okay, try to use formulae. Like you have to use formulae. I mean, try to put some thought in it. Okay. Okay. This is done. No. The same question. But I will teach from here. Okay. Same question, the same transformer of the previous problem. Another question is estimate the primary current in ampere when the load is 28 kilowatt at 0.8 power factor load. 0.8 power factor lagging. So what is power? Power is VRMS, IRMS, cos phi. Right? It has been given that power is 28 kilowatt. So VRMS, we just calculated how much? 1000. IRMS we have to calculate. Cos phi is given 0.8 lagging. So from here, can someone quickly calculate and tell me how much will be the primary current at this given load?
Thirty-five ampere.
35 ampere. Okay. And estimate the secondary current when the same load is applied. Again, into 2 we will do, which is 70 ampere. Right? Now, my question to you is, we have calculated that this much current will flow in the primary if we have a 28 kilowatt 0.8 lagging power factor load. What if the load is leading? What if the load is leading, 0.8 leading power factor load? How much will be the current?
That will be same, but direction is negative.
Direction will be the opposite, right? Okay. Now let us frame another question from here. The question is, I have kept the power factor constant at 0.8. Okay, I have some load where the power factor is constant at 0.8. The question is, what is the maximum kilowatt of load that I can supply? how to approach with this?
Rated power into
Rated what power? Apparent.
apparent power, rated
Yeah.
power into
Power factor.
0 point. Yeah.
So can someone please quickly tell me how much this value is?
Fifty-two
52,000.
52 kilowatt.
Kilowatt. So you see, this is why a transformer. This is why a transformer is never rated in watt. It is rated in kVA. See, when we are sending this 52 kilowatt power, can you tell me what is the primary current? You need not calculate, you can straight away tell. From here, it will be 65 ampere. Calculate. If you want to calculate. Isn't it 65 ampere? Do it this way, 52 into 10K equals 1000 into I1 into 0.8. Are you getting 65 ampere? Getting or not getting? You should get 52 by 0.860, you just did.
Yes, sir.
Okay. So you see, the transformer is rated at 65 kVA and it can deliver at this power factor a maximum of 52 kilowatt of load. If it had been rated for 65 kilowatt instead of kVA, someone might have put a load of 65 kilowatt at this much of power factor. That would definitely cause the transformer to draw a current much more than this, because 65 kilowatt is a real power. There is apparent power, there is reactive power also, because power factor is not unity. Okay, can someone find out how much will the primary current be if it is 65 kilowatt of power at 0.8 power factor? It is 65 by 0.8. 81 ampere current would flow. This would simply burn down the primary winding of the transformer. If you connect the load for a long time, it will simply burn down. That is why transformers are always rated at apparent power. Okay. If that is okay for everyone, we will go to the next problem. Read the question. A 200 volt by 160 hertz transformer has 500 primary turns. It takes 4.5 ampere current at 0.5 lagging power factor when energized on the high voltage side with no load. So this is a, what kind of test is this?
Open load,
Open
circuit test.
Open circuit test. Open circuit
no load
test.
test.
Yeah. So what happens in open circuit test? The current that the transformer draws is much, much less than its rated current, maybe 5% of its rated current. Okay. So in such a low value of rated current, in such a low value of current, you can safely neglect the copper losses that is happening in the transformer. So
only core
losses are important here. So while performing this open circuit test, this can be assumed as the equivalent circuit of the transformer, right? Now, it is done on the high voltage side of the load. Now, my question to you is this a good practice to perform open circuit test on the high voltage side of the load? Sorry, high voltage side of the transformer, not the load. Is it a good practice? No? See, when you are doing open circuit test, you are trying to find out the core loss, right? This is the supply voltage V. This is the resistance R. Your core loss is nothing but V squared by R. Okay. Instead of doing this test in this side, if I do it on the other side, say this is V1, I will apply V2. The same R will be obviously transferred here. No, these two I cannot draw at the same time. The same R will be transferred here, and I will get the same thing. Same power core loss I will get. So it doesn't matter from where I energize. But the thing is, if I am doing it from the high voltage side, why, like, say, this is only a 200 volt per 100 volt transformer. But maybe you can have, like in a distribution transformer, you can have some 11 kV by 400 volt transformer. So in this case, doing the core loss test, open circuit test on the high voltage side, you will require a 11 kV source. Whereas if you want to do the same test, you will get the same results if you do it on the low voltage side only with a 400 volt, which is easily available. So it's always a good practice, and it is always done, it's always followed, that transformers are open circuit tested on the low voltage side. But that hardly matters when we are doing problems, because as I explained, you will get the same core loss. So whatever. So when it is open, it takes a no load current of 4.5 ampere at 0.5 of lagging power factor load. Sorry, lagging power factor, this much of current it draws. Again, I have another question. Is this a good power factor? Say, if I say that there is a load of this much of power factor, 0.5, will you say that this is a good power factor load? Quick.
No, sir.
No. So this is not a good power factor. But the thing is, when the transformer is open circuit, this is drawing a no load current of this much of power factor. Can someone tell me why is this happening? Why is this power factor so poor in open circuit? Why is this power factor so poor in open circuit? Because you see, why do we at all need reactive power in a transformer? Even if the load is pure resistive, I will need some reactive power in the transformer. Why? That is to set up the flux in the core. Now I have removed the load. I have no load. I have some nominal core loss. But the same flux I have to provide in the core because I have applied the rated voltage. So right now it's a heavily inductive load. This XM, this magnetizing inductance is responsible for such a poor power factor when the transformer is open circuited. As soon as you connect a load, your power factor will improve.
working component absent, like
Sorry?
IW node is absent. That's why the power factor is very low, sir.
Sorry, what is absent? I couldn't understand it. What is
Sir,
absent?
working component IW, working component IW is absent in the open circuit test.
You
That's why
mean,
the
you
power
mean,
factor
you
is
mean
very
this
low.
thing? You mean this thing? This current?
The R flowing through the current through R.
Which are? These are?
Yes.
No,
Yes, sir. Yes, sir.
no. How can you say that there is no current flowing through this R? There is current. I have connected a voltage. There is a current flowing. It is present. But the thing is that when it's open circuited, this inductance, magnetizing inductance, this is dominating. This is very much high compared to, not very much high, very much low, since it's a parallel circuit compared to this R. This is dominating. This is a dominantly inductive circuit. This is a current is flowing here. I will call this ICL, I core loss, IM, magnetizing current, and a total INL, no load current. There is a current. This is because you don't have a load. The energy that is coming here is primarily reactive, or the power that is coming here is mostly reactive. That is why it's such a poor power factor. This happens in induction machine also. In induction machine at no load, the power factor is even worse. You will later learn why, or some of you might already know. Okay. The question is, estimate the rated maximum flux in milliweber. Any guess how to start with?
Maximum. The rated maximum flux we calculated by voltage equation, EMF equation of transformer.
We have the basic equation, the Faraday's law, right? d psi dt. Psi is n phi, n is constant, and definitely my supply is sinusoidal, so phi will be some phi max times sine omega t. Does not matter whether you take sine omega t or cos omega t. The phase and all will change, it does not matter. But since we are drawing, keeping this flux as the reference, take it sine. You can take cos also. Your conventions will only change, doesn't matter. So what I have is, I have n ddt of phi max sine omega t. So this will give me E equals n phi max omega cos omega t. So basically what we are getting is, there is a sinusoidal voltage and hence a sinusoidal flux. The question is, what is the maximum, what is phi m? So this E, you can see how we write voltage. We write voltage V as some V sine omega t or something, or V cos omega t something. So that is it. So this is the amplitude of the primary voltage. This is the amplitude of the primary voltage. Where is the primary voltage happening? I will quickly draw it once again. This is the amplitude of the primary voltage. So n phi m omega. So I will see what is the primary voltage, 200 volt, right?
200.
So n is how much? 500 primary turns. So can someone tell me the equation? How should I write? I am writing n equals 500. Tell me what I will write in place of E. I am writing the other side. N is 500, phi m, omega is 2 pi f, 2 pi into, what is the frequency? 60 f. What should I write in the place of E? What is E? The primary voltage is 200 volt. It's a 200 by 100 volt transformer. Quickly.
200 volt.
No, not 200 volt. 200 volt is the RMS. This is the peak value.
Okay.
See,
Okay.
just compare this.
Yeah.
E peak cos omega t equals this cos omega t. So E peak is equal to this. This is E peak. So how much? How much?
Root 2 into 200.
This much. From this, can you not calculate the maximum flux flowing through the transformer? Can someone quickly do and tell me?
When I calculate this expression, we have a maximum 15 milliweber. 15 milliweber.
Okay, I will just confirm this.
2.12 into 10 raised to minus 3.
Just a minute.
1.5 into 10 to the power minus 3.
No, it will be
Only 15 milliweber.
15. It will be 15.
Yeah.
It will be 15 into 10 to the power minus 3.
That is exactly right.
200 root 2 by 500. Oh, no, sorry. I made a mistake. 200 root 2 by 500 times 2 pi into 60. No, those who said 1.5, you are correct. It's 1.5. You see, you might have put the some of the value wrong in your calculator. It's 60 hertz transformer. I put 6 instead of 60, so I got 15. It will be 1.5 milliweber.
1.500 into 10 to the power minus.
1.5 milliweber. All right, so this part was easy. Now, can you tell me that at no load, this transformer has a peak flux of 1.5 milliweber in its core. How much will the flux be at full load in the core?
The constant, sir. Same.
Why constant?
Because when the load is applied, the extra current is drawn by the primary, sir. For demagnetizing effect is appear in the core. For that, extra current will drawn from the primary, sir.
So they will balance
from
each
the
other.
source, sir.
They will
Yes,
balance
sir.
each other. In
Yes, sir.
a ideal transformer, this holds good. Or if you want to be more general, Ni equals 0. N is the total number of turns. Okay, this thing I discussed in the last class in a good detail. All right. Okay, now we will go into it. So estimate, I will do one thing. I will copy paste the question once again here. Yeah. The next part is estimate the rated core loss or iron loss, whatever. The same thing. Quickly. You have a transformer. At least tell me what to do, how to start with. 200 volt, no load. It is drawing 4.5 ampere, 0.5 power factor.
That is the primary voltage into no load current into cos I naught, that is power factor.
But this is giving me the input power to the transformer. Input power to the transformer. Is it same as the core loss? We just discussed, it is same as the core loss. The copper loss is negligible in no load. This is the core loss. Now this part is interesting. Estimate the magnetizing component of the rated no load current. Okay, we will draw circuits now. Magnetizing component of the no load current. So if this is XM, this is RC. Okay, since we do not have any other X or R, I will write only X and R, okay? Or better to stick to the conventions. So this is the IM, this is IC, and they are vector summation. Vector summation is I.
Sorry for disturbing you.
Yeah.
The flow. Just I joined just now. Can you? If you don't mind, can you just repeat this problem?
Well, the problem is we have been given the rating of a transformer. It's a 200 volt, 100 volt, 60 hertz transformer,
Okay.
and it has 500 primary turns, and it is under a no load test. So, under no load test, it is drawing a primary current from the high voltage side, a current of 4.5 ampere and 0.5 power factor, a lagging power factor. Now the question is,
How you know, sir? It is from high voltage side. It is
it's
drawing.
mentioned in the question.
Okay.
The question is how much is the magnetizing component of the no load current? So the no load current which is flowing here, it is divided into two branches, IM, IC. And how much is the no load current? That is the question. So let us draw phasors, okay? Let us see if we can do something with phasors. Whenever you have questions like this, try to draw phasors. This is V1. So this is a parallel circuit, okay? Parallel circuit, all the components are having the same voltage across them. So voltage should be the reference phasor. In a series circuit, it's better to draw with a current reference phasor because all of them are having the same current. So this is the voltage phasor V1. Now can you tell me where will IC lie? Can someone tell me where will IC lie?
What is the question? What is the question?
I have drawn the phasor of V1.
Okay.
What will be the direction wheel of IC? The IC is this current flowing through this core loss component. This resistance, core loss resistance.
Lags the V, sir. Lag the V1.
Lags
I say
V1
lag
how
the
much?
V1.
How much?
V pi C, sir. Pi C. Lags V1 by pi C.
Pi C. Pi C degree or radian, how much?
In phase with V1, sir.
In phase with V1.
Degree.
In phase with V1. This is a resistance. I am supplying a volt, giving a voltage to a resistance. How can the resistance draw a lagging current? Someone said pi C degree. See, whenever you are writing some equation, always see whether the dimensions are matching. Pi C has a dimension of capacitance. How can it be degree? Degree is dimensionless. Okay, no problem with it. Keep trying. I mean, do not let that discourage you from answering further questions, okay? So IC will be in phase with V1. And how will be IM? How will be IM?
It's lagging, sir. Lags
Lagging
V1.
Perfectly like 90 degrees.
90
9
degree. To draw a perfect 90 degree here, I will try. Yeah. So this is IM, right? Now tell me, how shall I draw INL, the no load current, how shall I draw?
How it is lagging exactly 90 degree?
That is because this is a parallel circuit. You can see this is directly connected. This if I am applying a voltage V1, the voltage across this inductor is also V1. The voltage across this resistance is also V1. Now when I am supplying a pure reactive, a pure inductance, the current will lag exactly by 90 degree.
Okay.
Now tell me, how shall I
Sum
draw?
of IC and IM, sir.
vector sum of IC and IM. Sorry, I can draw it correctly. Yes. Yeah, so this is the INL. Okay, all of them are vectors. Now the question is, what is IM? Now can you tell me, what is this angle?
Phi node,
No, I want value.
value that
45 degree?
How much? 45? How do you say that?
40%.
I told 45 degree
No.
because it is, yeah.
Go on.
Since we are taking, so from the picture, I am able to understand that it is between both IC and IM.
This picture is
0.886 according to this question.
how much? See, in the
60
question,
degrees.
how much? Go on, how much?
Sir, I think it's 60 degrees.
60 degree, it will be 60 degree. See, in the question, it is mentioned that it is drawing a power factor of, sorry, Tapas, I can't hear you. Your voice is breaking. Tapas, you can write in the chat. You can write in the chat. I will see. Tapas, please write in the chat. Sorry for that because we are short on time. Okay. So 60 degree because it's given in the question already that the no load current is at 0.5 lagging power factor.
Yeah.
It's 0.5, so it will be cos inverse 0.5. 60 degree.
I have doubt. The no load current lagging by 0.5. Since the load only inductor is there, that is why we are writing 0.5 cos phi. That is 60 degree. Correct? Am I right?
No. It doesn't matter what the load is. We have been told in the question that current is lagging by a power factor of 0.5. So it does not matter. We do not even need to see what load is there, what components are there. Definitely there is inductive component. But if it is 0.5 lagging, we simply have cos inverse 0.5. 60 degree.
Okay.
So there are two currents. One is in phase, other is in quadrature, and their resultant is 60 degree lagging from the supply voltage. Right. Okay. Now we have done a lot of phasors. We will come back to the question. The question is estimate the magnetizing component of the rated no load current in ampere. Magnetizing component of the rated no load current in ampere. We should be able to do it from this.
I load into sin phi node.
Forget formula. Let us try to derive. I have forgotten formula. I started this thing 7 years back.
According to the phasor.
Okay. See, this is the I no load, right? The length of this thing is I no load. Okay. Can we not find the length of this IC? Can we not find the length of this IC?
Yeah, we can do V divided by RC. Will give you the magnitude of IC.
V by R will give us the magnitude of RC. Or since we already have the power loss in the resistance, we will simply do V squared VI.
Not able to see the question.
Sorry?
Not able to see the question. Yeah.
Since we have already calculated the power, 450 watt is the core loss. So we can simply write VI equals 450 watt. Notice I am not writing VI cos phi or anything because I know it is a pure resistive. This 450 watt is loss of this resistance. So VI is 450. My V is 200 volt.
So where it is mentioned 450 loss of,
We calculated this, that at no load, it is drawing a 4.5 ampere current at 0.5 lagging power factor.
okay,
So this is the loss, this is the core loss here.
okay. Okay.
So since we already know this, Vi equals 450 watt, I can calculate this I is nothing but IC, 450 by 200.
Hmm.
By 200. This will be 2.25. Sorry, ampere. So I have a triangle like this, where this is 4.5, this is 2.25, this is 60 degree, this is 90 degree. I have been asked to find out I am just drawing this triangle, okay? So I have been asked to find out this. Say this is x. Can I not find out x?
Yeah,
This is simply x by 4.5 is equal to sine 60 degree. Or in other words, x is 4.5 sine 60 degree. You will get something root 3 by 2 times 4.5, whatever is the value, that is the value.
3.897.
3.897. Since we have, here we did not require this value. We directly calculated from this. There was another way also, which is simply 4.5 squared minus 2.25 squared. That would again give the same value. Okay, we did not calculate this. We already had enough data. Any doubt in this? Okay, we are already out of time. Siva will take doubt clearing class on Tuesday 7 p.m. He will discuss some more questions there. And for now, if you have any more doubt, a general doubt, you can ask about the technical things, obviously.
Sir, it may be a silly question, but sir, in short circuit test, in AC test, we are connecting a wattmeter in the HV side only, sir, not the wattmeter is not in short circuited path. It is in the primary only, sir. So we can calculate that one in WSC power.
Okay.
The reading.
So, okay, I've got your question. So,
Yes, sir.
sometime back we discussed that we do open circuit test in the high voltage side, right? I explained why so. Now the question is, where to do the short circuit test? Okay, so what happens in short circuit test? I have a practical transformer. Okay, I short circuit this. Connecting an ammeter is same as short circuiting. Any doubt about that?
Okay. No, sir. No, sir.
And I apply a voltage, some voltage here. The question is how much voltage? See, my target in short circuit test is such that the maximum copper loss happens, or the rated, not maximum, the rated copper loss happens in the transformer. That is, the current flowing through this must be I-rated, right? Now, instead of this ammeter, I could have put a load here also. I could have put the rated load here also. The rated load would also draw the rated current from the supply, but that would cause a lot of power flow from the supply. Not only the losses, but also the load power. That is why, since my target is to find out only the core loss, I do not need, the copper loss. I can simply push the rated current through it and get the copper loss. So this is the rated current.
So one doubt. So But you are saying if you put a resistive load or load, power loss is more. How it will be? It will not be, no. So power loss across the resistance you are saying load.
Yes, the overall load will be more.
Okay. Got
Overall
it,
loss
got
will
it.
be more.
I
In
got
that case, it is possible that you segregate. But this much is the load power and this much is the loss. But why waste so much energy? That is why the short circuit test, firstly. Secondly, what about the rated current? Say, if I compare the rated current in high voltage side and in low voltage side, which one is more? Which one is more?
I will
Low
listen.
voltage, no, low voltage side rated current is more.
Voltage is,
Yeah. Here in this case, low voltage is more. Yeah, because we shorted.
No, in any case, in any transformer, see, we have V1 I1 equals V2 I2, right? So this product is a constant. So if I have a large value of V, my current will be low. Power is same on both the sides.
Okay.
If I have low voltage, for the same power, I have to have more current.
Yeah, correct.
So low voltage side, I have more rated current. High voltage side, I have lesser rated current. This is low. So when I was discussing this thing, why open circuit test in high voltage side, I said that why go for a unnecessarily high voltage source. Similarly here also, if you want to do the short circuit test in the low voltage side, you can do perfectly. You will get the same results, but you have to have a source that can supply such a high current. But if I do it on the high voltage side, I will not require that much of current. I can do it with a small source that has a very limited current rating. That is why short circuit.
actually, excuse me, sir. Actually, my question is, I am connecting the wattmeter in the high voltage side, sir. I am shorted in the LV winding, sir.
Yes.
The
Now,
showing the reading is whether it is a short circuit power or not, sir. That's my question, sir.
so if you have
Yes,
a wattmeter
that
like
only,
this,
yes, sir.
see, this is a practical transformer, okay?
Okay, sir.
This is short circuited. Now, if I say I connect another wattmeter here,
Okay, sir.
suppose I connect another wattmeter here, how much will this wattmeter read?
Same power.
This wattmeter will read 0.
Okay.
Why? Because it's a short
Yes, sir.
circuit.
Short circuit. There is no
Short circuit
current.
consumes-
Current only. There is no voltage, sir.
Short circuit consumes no power.
Yes, sir.
So if you are having a supply voltage here, which is supplying the copper loss to the transformer, you have to have the wattmeter here such that it can measure the current supplied by the source and the voltage of the source. Then only you can get the power supplied by the source, isn't it?
Okay, sir.
Sorry, voice got disturbed. Can you repeat what you said last circuit diagram, which is actual transformer?
I said that this is the practical transformer. We are doing short circuit test on it. His question was why the wattmeter on the high voltage side. So this is the high voltage side. This is the low voltage side. So
Okay.
I asked him that even if I connect a wattmeter in the low voltage side, how much will it read?
0,
It will
because
be
not,
zero.
not
There is short
power.
circuit. I want to measure the power supplied by the source.
Mm.
So I have to measure the current from the source, which will be done by this current coil of my wattmeter. And
Yeah.
I want to measure the voltage of the source, which will be done by this pressure coil of my voltmeter.
What is that pressure coil?
Yes, voltage coil of wattmeter is traditionally called pressure coil.
Okay.
PC.
Okay, sir. Thank you, sir.
Yeah. If anyone has any more questions, only 2 or 3 people talk today. All right. then.
Sorry, I just, because after a long time I'm studying.
No, sure.
Sorry, the pressure coil, what you said, pressure coil of what meter is pressure coil?
See, I am measuring power. What?
Yeah.
What is
Yeah.
voltage times current?
Current, correct.
Let us not talk about power factor for now. So,
Yeah.
voltage times current. So, or maybe say cos phi. So,
Possible, yeah.
I have to measure both the voltage and the current,
Yeah.
so as to see the power consumed by the load. Say this is the load. So if I want to measure the current, what do I need? I need an ammeter. Ammeter is
Ammeter.
in series with the load.
Correct.
And I want to measure the voltage also.
Hmm.
So that will be kept in parallel to the load.
Parallel to the load, correct. That will be a drop across the load, correct.
Sorry, my
Something.
sorry, my OneNote crashed. So this coil is the current coil.
Yeah,
This is measuring the load current.
Yeah. Load
And this coil, which is the pressure coil. Actually, why this is traditionally called pressure coil, we know this thing. If we have two columns of water, the one with high pressure will send the the pressure is taken as the equivalent of voltage. So this is traditionally called pressure coil in wattmeter PC.
Okay. This is a kind of an inductive coil, you are telling.
These are all inductors,
Okay.
coils.
Okay. But we can even put a resistance there, no? To measure the voltage. Example.
No. Actually, what happens is actually we are going into measurement point. What happens is in any ammeter or whatever, we have two permanent magnets, and we have a coil. This coil is nothing but this coil.
Okay.
Now, when some current is flowing through it, this is creating a torque T.
Okay.
This torque, there is the pointer. This torque is moving. The pointer is connected somewhere here.
Okay. Got it.
And
Thank
it
you,
is
sir.
spring loaded. This is spring loaded. So once you remove this, it again comes back.
Comes back. Okay. Thank you.
Yeah.
Yeah.
What is PC? PC, what PC?
Sorry. Could you please repeat? Lakhan, could you please repeat? All right, then you make sure to attend the Siva's class. He's one colleague of mine at IIT Bombay. He's also one tier of this course. He'll be taking class every Tuesday, 7 to 8. He will discuss some more questions there. And if you have more doubts, you can ask him. He will clear them too.
Sir, is it not possible to change the Tuesday to Wednesday, sir? Because
no, actually, we have been told by NPTEL that we cannot change slots.
okay. Even the timing also not possible?
No.
Okay. Instead of starting at the 7:30. Okay.
No. Actually, we have already distributed the slots, so you can.
Okay.
Okay, all right then. These videos are recorded and uploaded in YouTube. I think you have already seen in NPTEL page that you will get the links to these videos. If you want, you can rewatch them. I will stop presenting. Okay, thank you for attending. We will meet once again. Next Tuesday. Saturday. Next Saturday, 7 p.m.
Thank you, Mr. Dev. Very good understanding, learning today.
Thank you.